Hello everyone, my name is Meng, come from Chongqing University. Today I'm very glad to share our paper, EffortAware Just-in-Time Defect Identification in Practice, a case study at Alibaba. This paper is cooperated with Dr. Zhang from Monash University, Dr. Fan from Zhejiang University, Professor Luo from Singapore Management University, Professor Hassan from Queen's University, Dr. Zhang from Alibaba. First, what is just-in-time defect identification? Other studies may also call it as just-in-time defect prediction. Such technique aims to identify defective change just in time. In general, we can learn a prediction model from historical labeled changes with diverse change features. When receiving a few new changes, the model can identify defective changes and provide a defective list for manual inspection. Since JIT defect identification is performed on changes, such technique is also called as change-level defect identification. Compared with traditional module-level defect identification, the granularity is different. Module level aims to identify defective module, file, or classes. Such kind of identification suffers from several issues. First, it is coarse-grained. Although it can identify defective modules, developers may also need to inspect a large amount of lines of code. Second, it cannot provide a context, such as who do the defect be introduced and who introduced the defect. Change-level identification aims to identify defective changes. Such identification can bring a few benefits. It is fine-grained. Developers can focus on inspecting the changed code. It can be performed just in time, which can ensure the context is still fresh in developers' mind. Such fresh context can help to fix the defects early. In order to satisfy the real-world scenario, effort-aware JIT defect identification has been proposed in recent years. Effort-aware model aims to discover as more defect changes as possible, with limited inspection effort. The basic idea is that the more lines of code modified, the more effort required to inspect the change. Usually, the effort cost for inspecting a change is estimated as the AOC modified by the change. A typical effort-aware measure is how many defective changes can we find when inspecting 20% AOC modified by all the changes. Here is an example of effort-aware model and measures. Suppose there are 100 changes, 1000 AOC modified totally, 10 defective changes among them. If we inspect 200 AOC, we can inspect 40 changes. As a result, 4 defective changes are found. The recall is 0.4 and the precision is 0.1. Many effort-aware approaches have been proposed. Such approaches can be classified into two categories: supervised approaches such as EALR, OneWay, and CPS+, unsupervised approaches such as LT and Chain. Due to the effectiveness on open source projects, many companies have noticed such technique. At Alibaba, there are increasing lines of code, increasing changes per day, and increasing requirements for software quality. Code review is a significant and challenging task. They are very interested in effort-aware JIT defect identification effectiveness. However, the effectiveness in practice is rarely investigated. Thus, our central research question is, how effective is effort-aware JIT defect identification in practice? To that end, we designed a case study at Alibaba. First, we collect projects with labeled changes and change features as a dataset. Second, we implement 5 approaches as our candidates for applying at Alibaba. Third, we apply the best performing approach on Alibaba projects and investigate the important features. Then we investigate the association between project factors and defective changes. Finally, we design a user study to investigate the effectiveness in developers' eyes. Here is our case study setup. First, we select 14 Alibaba projects with 14 change-level features. We implement prior approaches with their same pre-processing steps. In terms of the evaluation measures, we adopt two groups of measures. One is considering the inspection budget as 20% of the total change LOC, such as precision recall at 20%. The other group does not consider the inspection budget, such as FSE and AUC. In our evaluation, we use a time-aware validation setting, which uses the prior changes to predict the future changes. Our experiment is designed to answer these three research questions. Lucky one, how effective are state-of-the-art supervised and unsupervised EffortAware JIT defect identification approaches when applied on Alibaba projects? For answering RQ1, we implemented these 5 state-of-the-art approaches on Alibaba projects to investigate their effectiveness, including 3 supervised and 2 unsupervised approaches. This table presents the effective results with statistical tests on the 4 measures. In summary, CBS Plus performed best in most of the cases in terms of the above measures. From the results, we have the following findings. First, if following the identification results by CBS Plus, developers can inspect 29% of the changes to identify 48% of the defective changes with a 37% precision. And developers inspect nearly 5 changes before they finding the first truly defective change. Second, chain sacrifices precision at 20% to achieve a higher recall at 20%. When considering the F1 score, Churn no longer outperforms CBS Plus. In addition, Churn performs very poorly in terms of IFA. Third, most findings on supervised with unsupervised approach on Alibaba projects are consistent with on open source projects. That is, CBS Plus is the best performing approach. Thus, we choose CBS Plus as the approach to deploy at Alibaba. Article 2. What are the important change-level features for EffortAware JIT defect identification at Alibaba? Do these important features differ between Alibaba and open source projects? For answering RQ2, we identify important features by the following steps: removing highly correlated features, redundant analysis, permutating analysis, and SKESD test. After that, we select 10 widely used open source projects to investigate the important features with the same method. Then we can observe the differences between Alibaba projects and open source projects. This table presents the important features results. The empty symbol means that the feature is correlated with other features and it is removed. The top, second, and third most important features are highlighted in an orange, green, and blue background. As a result, we can find the same top most important features and the differences in terms of the second and third most important features between Alibaba projects and open source projects. Article 3 aims to investigate the association between project factors and defective changes. First, we collect different project-specific factors, such as size, user base, ratio of defective changes. Second, we use a mixed effect model to express the relationship between likelihood and change features. while accounting for the different project-specific factors with these two R packages. The association results indicate that, first, the mixed effect model can explain the variability of the data, 31% better than the model with only using change factors. This indicates that the project-specific factors have an impact on the defective likelihood. Second, the total LOC changes, mean change size, and defective ratio project factors are highly associated with the defective likelihood. Finally, we designed an user study to answer the question, how effective is our EffortAware JIT defect identification tool in a real-life industry setting at Alibaba? In the user study, we choose the changes in recent months in project P1 as the scope for manual inspection. As a result, 205 changes are analyzed by using our tool. With the limited inspection effort, 5 participating developers are invited to check the warned 33 changes. Then we synthesize their responses. Before performing the user study, the participating developers were told that defective means that the change will introduce risks, such as may lead to future bugs. Such risks would cause a negative impact on their products and processes. Developers believe that additional attention is needed in the form of careful code or design reviewing or more testing. Clean means that the developers consider the change to be of low risk. Unknown means that the developer has no strong opinion towards that change, or that the developer does not have enough experience to make a choice. From the user study, we found that, first, the tool's warned defective changes are correct in the 33% of the time. Second, our tool helped developers focus on only 33 of the 205 changes, costing 20% of the entire effort required to inspect all the changes. In the future, more case studies and more companies are needed. Additionally, more feedback from developers are needed to improve the effectiveness and the practicality of EffortAware JIT defect identification further. In conclusion, in this paper, we conducted a case study at Alibaba for investigating the effectiveness of EffortAware JIT defect identification in practice. Additionally, we conducted a user study to investigate the effectiveness of the best performing approach in a real-life setting at Alibaba. That's all. Thank you for your attention.